The second comparison test that we're going to look at for this section is called the limit comparison test. And the requirement for this test is that once you get to a certain n value, so it says for all n greater than or equal to capital N. So once you get to a certain point, all the values of your two series that you're comparing have to be positive. Okay, so you could have a few negatives at the beginning, but once you get to a certain point, all the values need to be positive. When you're using the limit comparison test, your series A sub n is going to be the series in question. B sub n is going to be your known quantity. And that known quantity is what's going to always go in the denominator when you do the limit comparison test. And if you look at the limit as n goes to infinity of A sub n over B sub n, if that limit is a number c, a positive number c, then either both series converge or both series diverge, okay, depending on whether B sub n converges or diverges. If, when you take A sub n over B sub n and then look at the limit as n goes to infinity, if you end up with 0 and that denominator series B sub n converges, then so does A sub n. And then finally, if when you take the limit you get infinity and B sub n diverges, so does A sub n. That's how our limit comparison test is going to work. And again, B sub n, what goes in the denominator is going to be the known quantity. The P series are going to be very, very useful for these. So I'm going to go through a few examples to show you how this works. For the first one here, we're looking at the series from n equals 1 to infinity. We have 5 to the n over the square root of n times 4 to the n. So I'm going to compare this with the series 1 over the square root of n, or 1 over n to the 1/2 power. Oops, there we go. Now this series is going to diverge because it's a P series with P equals 1/2. And with the P series, anytime that P value is less than or equal to 1, the series diverges. So my suspicion is that this one is going to diverge as well. So let's look at the limit comparison test. I'm going to take the limit as n approaches infinity. And I'm going to take this entire term. So we've got 5 to the n over the square root of n times 4 to the n. And in the denominator, it's going to be 1 over the square root of n. So you could leave it like this and cancel out your square root of n. If you would prefer, you could rewrite this as a multiplication. So you'd have 5 to the n over the square root of n times 4 to the n, and then flip your denominator. But either way, you're going to be able to cancel out the square root of n. What you're left with is the limit as n approaches infinity. And I'm going to rewrite this. Instead of 5 to the n over 4 to the n, I'm going to write it 5/4 to the n power. As n approaches infinity, because 5/4 is greater than 1, so basically we've got a geometric series here with r greater than 1, this is just going to keep getting bigger and bigger and bigger, and it's going to also go to infinity. So we're in the third case here. The limit equals infinity. The denominator diverges, so does the series in question. So we can say, when we're looking at the series from 1 to infinity, 5 to the n over the square root of n times 4 to the n, that will diverge. And that's how the limit comparison test works. So let's look at a couple more examples. For the second one, we're looking at the series 2 to the n minus n over n times 2 to the n, which is a bit of a mouthful. In this case, so you'll notice I'm kind of focusing on the denominator. And what do I have? N-wise in the denominator. Here I just have an n. So that's what I'm going to compare it with. I'm going to compare it with the p-series 1 over n. Now we know in advance that 1 over n is going to diverge because it's a p-series with n equals 1. So I've got a suspicion that this series here is also going to diverge. So let me look at the limit as n approaches infinity of this 2 to the n minus n over n times 2 to the n over 1 over n. And I'm not going to take the time to rewrite it, but you could rewrite it as a multiplication. And when you do that, it's going to allow you to cancel out these n's. So I'm left with 2 to the n minus n over 2 to the n. What I'm going to do is I'm going to divide that out. 2 to the n over 2 to the n is just 1. And then n over 2 to the n is n over 2 to the n. Now, as n goes to infinity, 2 to the n grows larger faster than n does. So this second fraction is just going to go to 0. So the limit here is going to be 1. We're actually in, and I'm going to scroll back real quick, we're actually in the first case. Here, when we take the limit, we do get a positive whole number. However, because the series in the denominator, 1 over n, diverges, so does the series in the numerator. So since 1 over n diverges, we can say that our series in question also diverges. And I'll go ahead and write that out real quick. So you can see these tests actually don't take that long to do the actual comparison tests. And we'll do one last example. For this one, we're looking at the series from n equals 1 to infinity of 1 over 1 plus 2 plus 3 and so on up to n. Now, 1 plus 2 plus 3 all the way up to n, we can write that as an algebraic expression. That's the same thing as n times n plus 1 over 2. So this is the same thing as saying 1 over n times n plus 1 over 2. So that's the same thing as saying 2 over n times n plus 1. Or if you want to multiply it out, 2 over n squared plus n. Okay, these mean the same thing, and they're all from n equals 1 to infinity, just because I don't feel like writing all that out. I didn't, but it's holding true the whole time. So what am I going to compare this one to? Well, I'm going to compare it to 1 over n squared. Okay, that's our largest exponent in the denominator. Once again, we have a p-series. In this case, though, the p-series is going to converge because the p-value is 2. 2 is obviously greater than 1. So we're going to look at the limit as n approaches infinity of 2 over n squared plus n over 1 over n squared. This one I will, whoop, got a little excited there with my m. This is the limit as n approaches infinity of 2 over n squared plus n times n squared over 1. So we have the limit as n approaches infinity of 2n squared over n squared plus n. I'm going to divide everything through by n squared, so that's going to give me the limit as n approaches infinity of 2 over 1 plus 1 over n. As n approaches infinity, 1 over n is going to go to 0, so we have 2 over 1, which is just 2. And once again, we're in the first case. So since we get a positive integer here as our answer, and the series that we're comparing with converges, the series in question is also going to converge. So we can say, since the series 1 over n squared converges, and that's n equals 1 to infinity, and the series that we've been given is also going to converge. And those are your comparison tests.